Okay. My name is Till Hofmann, and this is joint work with Niemueller and Gerhard Lakemeyer, and I'm going to present this work on generating macro actions from a plan database for planning on autonomous mobile robots. So I'll start with a motivating example. On the right, you can see our domestic service robot Caesar in our lab, and Caesar's task is to clean up a table of dishes, which you can see on the right. Basically by just putting dirty dishes into the dishwasher and clean dishes onto the counter. It has, in the simplified versions, it has 4 actions that we can use, which are go to, align, back off, put, and pick. Sorry, it's 5. But for this talk, we will focus on these 2 actions, go to and align, because we can show all results on just these 2 actions. So, planning in robotics. The problem with planning in robotics is that planning on a robot is very long planning times are not good because it makes the robot really unresponsive. So even if the planner only thinks or plans for like 20 seconds, for the user it is a very undesirable experience. So fast planning times are particularly important in robotics. The problem is that planning often takes a long time, and if you use approaches like continual planning, where we interleave plan generation and plan execution, the agent actually has to plan very often, which makes the whole situation even worse. But on the good side is, if we look at continual planning, we see that very often we plan very similar problems or even the same problem over and over again. So the question that arises here is, can we reuse previous plans to speed up further planning runs? And of course the answer is yes, it is macro planning, and the idea in this talk is to use a database full of plans to generate macro actions, and we generate those macro actions from action sequences that occur frequently in our database. So as an example, in lots of our plans, we have the sequence go to align, and we just merge this into one macro action and use that for further planning runs. And of course, we only want to use macros that are helpful, and the metric here that we use is frequency. Our approach, DBMP, allows macro generation offline. This is nice in robotics because we have ample of resources offline, but we have only very, very limited resources online. And we represent macros as PDD actions, which has the advantage that we can actually just swap the underlying planner without any modifications to the planning system. In the following, in this work, we restricted ourselves to strips domains. So this is the general architecture and an overview of our approach. You can see that here we have a planner with a domain and a number of problems, and we collect all the planning results in a database. From this database, we then identify frequent action sequences, which are then candidates for macro actions. From these candidates, we generate macro actions, which are PDDL representations of those action sequences. We add the macro to a domain to obtain an augmented domain, which can then be used for further planning runs. And in the following, I want to go into more detail, mainly on number 2 and number 3, the identification and the generation of macro actions. So for the identification, the goal of the identification, as I said, is to find frequent action sequences in the database. And for that we use MapReduce. MapReduce is a programming technique which allows to process and generate large data sets. And in general, in MapReduce, you split up the whole operation into 2 steps. In the map step, you take one input pair and produce a set of intermediate key value pairs, which are then again reduced to a final data set by the second step, the reduce step. So if you look at our example, PDDL plans, then our map step is that from a single plan, we get all occurring action sequences, including all subsequences with all parameter assignments. And then in the reduce step, we just count all these action sequences over all plans. So this is how we use MapReduce to identify macros in our plan database. Here's an example. So let's say we have two plans in our database. The first plan is go to from hall to kitchen, and the second one is to align in the kitchen to the dishwasher. And the second plan is that we go from the hall to the table, and then we align from the table to the table. So the line action, basically what it does is you have a rough localization, but in order to do any manipulation tasks, you actually need to have very precise localization. So the align action just makes sure that you're precisely aligned to the second argument, which is here the dishwasher and here the table in the living room. So starting with the first plan, we can identify from this plan the action sequence go to align, and here we have grounded actions, but at the end, of course, we want to have action operators, so we need to come up with parameters for this macro. And here's really one of the key points of DBMP, that we don't just use one new parameter for each parameter in the original action sequence, but for example, here we can see that kitchen and kitchen is really the same parameter in this case. So in our macro action, we will encode it with the same parameter. So the final macro operator will only have 3 instead of 4 parameters, which the original action sequence had. Then we go to the second plan, and of course we can see the second plan is also an instance of this action sequence, because we can assign hall to P1, table to P2, table to P3, but also P3 to table. So plan 2 is also an instance of this sequence. But we can also see that there's actually another sequence that we can get here, which is also go to align, but only with 2 parameters. So here we can see we use 3 parameters because the last argument of align was different to the first argument of align, while here in the second plan we have table table, which we can use for the same parameter. So at the end we have 2 different actions, well, the same action sequence but with different parameter assignments, which we can then use in the next step to generate a macro representation for this action sequence. So the goal of the macro generation is to, from the sequence of action, generate one precondition and one effect that summarizes the whole action sequence. That is, that at the end we have one PDDL action which represents the whole sequence. And in order to do that, we do for the precondition we use regression, and we do this by regressing each precondition over all preceding effects, and at the end we get one precondition, and for the effect we chain effects starting from the last action going to the first action, and remove any conflicting effects. And instead of going into detail here, I just want to show you one example. I'll go to a line example again with 2 parameters, where we can see that a line had as precondition that the robot has to be at location P2, but it's not a precondition here because that's actually the effect of go-to. So the precondition of the align simplifies here. And we can see that the resulting precondition is the precondition of go-to, and the remaining precondition of align, which is that P2 is alignable to P2. Similarly, for the effect, we can see that we have a combination that the robot is not at P1 anymore, but at P2, and it's aligned to P2. Coming to the evaluation, so to evaluate our approach, we used 3 IPC domains, namely blocks, world, hiking, Bauman, and we also used an example from the Logistics League, and we compared our approach to Fast Forward without any macros, Marvin, which is an online macro planner, and MacroFF, and they are the SOLAP configuration. So for the blocks world domain, we can see, Oh yeah, I should mention we used fast forward for seeding, and we used a single macro of length 2 for this domain. And we can see here that macro of F performed the best. Marvin still performed better than DBMP, but we have at least better results than fast forward. So here the other two approaches are actually an advantage. Coming to the next domain, hiking, we can see that our approach, DBMP, performs the best, starting from like giving 4 seconds of planning time, and it can solve the most problems. So it can actually solve 95% of the problems in the given time limit of 30 minutes. Then as a third domain, the barman. This is kind of special because we actually use fast downward for seeding and then use fast forward for planning. So this really shows the advantage of just swapping the underlying planner. So we use fast downward to compute good plans for seeding, and then during the actual planning we use fast forward. And we can see that here DBMP performs much better, which has one simple explanation, namely that fast forward couldn't solve any of the problems, meaning that macro of F could also not solve any problems because it builds on top of this. And Marvin was able to solve some problems, but only with a much longer planning time. This is again an overview, which are basically the results I just showed. I just want to point out one thing. We also used a combination of 2 macro planners, namely DBMP and Marvin, which performed okay but didn't really show a huge advantage. But if you look at the barman domain, then this was actually the only combination of planners that was able to solve our problems. And we can see in the logistics domain that our approach performed reasonably well because it had a short mean planning time, but it also could only solve 4 of the 81 problems. So there's still room for improvement. Summarizing, database-driven macro planning has the following approach. We collect previous planning results in a plan database. From this database, we then identify frequent action sequences. We generate macro actions from those action sequences and represent them as PDDL actions. And we use those macros then to plan with the macro augmented domains for subsequent planning runs. For future work, we want to extend this to ADL because we have some robotics domains that require ADL and we could not use this approach for this. And also there's the open question, how do we actually select good macros? Because right now we just use the most frequent macro and only one of length 2, but of course we could add multiple macros of bigger length. So summarizing database-driven macro planning, the idea is that we improve planner performance by adding macro actions based on frequent action sequences in a plan database. Thank you very much.
Questions?
I'll speak loudly.
Okay.
For slide 7, did you consider using frequent pattern growth algorithm, the frequent pattern growth algorithm?
Nope, I don't know this algorithm.
It's just a tree-based way of accumulating.
Okay, what is it called?
FP growth.
FP growth, okay, thanks.
So I might be asking a similar question, but a lot of times we have a partial order between the actions rather than sequence. So have you tried looking at that?
No, so there are some approaches in MAM by Kupar et al. Who identify independent actions and that they can actually swap, but we have not looked at this here.
More questions? So is the average length, I don't know if you put it out in the results, the average length of the macros that you learned? Are they like short macros?
In this evaluation,
yeah.
We only used macros of length 2.
Of length, oh, okay.
Yeah.
So in the robotics domains, you might have numbers. Would that affect the way which you compute the macros? You don't have numbers on the action descriptions?
No, we don't.
Like costs?
No. So for action costs, we could actually just sum the costs of the two of the actions in the sequence to get the cost of the overall macro. So that would be, I guess, feasible. Yeah.
Any more questions? Okay, so let's. Patrick.
So in the panel on 2 days ago, Rao was asking, should we be building databases of plans and making them available? So I'm just wondering, is your database open to the public?
Not yet, but it will be.
Okay, so let's thank the speaker again.